Let's look at a new phrase known as inductive reactance. Before understanding the entire phrase, let's take up reactance. See, when we have a resistor present in AC or DC or AC, it behaves the same. When we talk about an inductor, in DC and in AC, they don't behave the same actually. The behavior in DC, direct current, and in AC, the behavior is different. To be honest, we can tell your inductor offers some kind of resistance to AC rather than DC. DC it does, but not to the extent of what it does to AC. Right? Similarly, we have something called as capacitor, right, which you guys already know of, but still. So there is something called as capacitor, which also behaves in a weird way when it comes to DC in comparison to AC. With AC, it behaves differently. With DC, it behaves differently. So we have a phrase called as reactance, which talks about this. Reactance is a measure of the opposition that a current element, such as your inductor and capacitor, present to the flow of alternative current. It is similar to the resistance, but specifically applicable to your AC circuits. So you can imagine a reactance as a special kind of resistance that shows up only when we have AC current. As simple as that. Whenever we have a AC circuit, your reactance comes into picture. It is either from a capacitor or from an inductor. When it's from an inductor, it is known as inductive reactance, as simple as that. So the basic idea of inductive reactance is it represents how strongly an inductor opposes the flow of alternative current. Okay guys, so here the basic definition in terms of definition, the key phrase here is flow of alternative current. Now, official definition of inductive reactance. It measures the effective resistance or opposition that an inductor presents to the flow of alternative current. The same thing, whatever we discussed, that is your definition as well. Now, how do we represent it? Excel. That's how we represent that. So mathematically, how does it look like? Well, if you guys remember, we have an instantaneous current given by this particular expression when it comes to an inductor, where we substituted I naught as your E naught by I used E naught in the last video, so let me stick to that, by omega L. Okay, then if you compare this with, right, comparing with actually ohmic relation, which gives us V is equal to IR, right? So, or I can write it as I is equal to V by R. So, voltage, omega L, R. So, what can we tell? Therefore, we write it here. Your XL is equal to omega L, right? Does it make sense? Denominator, XL is equal to omega L. Okay, guys. Now, okay. And by the way, omega can be written as 2 pi FL. So, making use of this, let's pick up a specific scenario. I spoke of, the behavior of inductor in DC is a bit different, a lot different actually. So let's look at that. So in DC, what is your frequency? Frequency of oscillation is 0, right? So what will be XL? XL will be 0. Does it make sense? XL will be 0 because 0 into entire expression is 0. Actually, when you look at a RL series circuit, so basically it's nothing but you have a resistor, you have an inductor connected to a AC source and DC source, right? The graph, it looks in this manner. So till say this point, somewhere till this point, there is some kind of resistance because of your inductor, it's very minute, for fraction of second. And after that, your flow of current flattens up. So this is because of presence of, because of our inductor, right? And after that, it behaves as if, there is no resistance. At least not because of, no resistance because of your inductor. But yes, we just theoretically, we write it as 0. But of course, we use it with the resistor and obviously other components. So this is how it behaves. Again, this is specific to RL circuit. This set of cases purely inductor based. Now, one last conclusion regarding the same, that is that specific case. After a fraction of a second, it acts like a wire with no resistance to flow of current. What it means is the inductor offers no resistance to flow of current after a certain point. When I tell it, we mean inductor. So XL is equal to 0 for DC is what it means. Now, one more thing that we need to know is how will XL vary with frequency. So clearly from this, XL is proportional to frequency. It's linearly proportional. So when it's 0, it's 0. And we have this. Right, guys? So that's your XL being related to frequency. Okay, so yeah. So what we just learned now was, we have seen the weird behavior that is offered by our inductor to AC current. When it comes to DC, it's a simple straightforward scenario. Gradual increase and flattening out of the presence of inductor. It acts like as if it's not there. But when it comes to AC, the behavior is different. Right? It offers some kind of resistance to whatever is happening to the circuit because of AC. And that is given a special name called as reactance. Specific to your inductor, it is known as inductive reactance. And when it comes to capacitor, we'll be seeing that. So by the way, it is XL. Oh yeah, sorry, X is meant for reactance. XL means with regarding to inductive reactance. This is right. And the math is quite simple. And the definition is all simple. And when it comes to DC, the inductive reactance is 0. So it acts like as if it's not there. And it is linearly proportional to its frequency. The frequency at the AC source. Yeah.